Hello and welcome back to the second session for ICFP 2020. And our next talk is going to be Kindly Bent to Free Us, and it's going to be presented by Gabriel Radan.
Hi everyone, so I'm Gabriel Radan and I'm going to talk to you about memory and safety for a little while. Here is a report provided by the Chromium team about high severity security bugs in Chromium, and you can see that almost 2/3 of the bugs in Chromiums are memory related and 1/3 of the bugs are simple use after free errors. So you could say, okay, Chromium is written in a mix of C and C++, and surely this bug don't happen in high-level type languages, right? Let's write some OCaml code. Here is a small example of code where we open a database, we write a database of grades, we write some grade in the database, the mass grade, we close the database, then we try to read the literature grade and print it. So the OCaml type checker will happily type check and compile this program, and later on we will have a runtime error. So there are various ways to deal with this kind of errors, and today I'm going to present AF, which is an ML-like language that prevents precisely this kind of error. So here is the same program written in AF. It looks very much like the ML program, the OCaml program from before, except this time when we reach the last line, then the type checker will refuse at compile time this program. So we have a few specificity in AF. The first one is that we use kinds to determine usage. So here the grade database is of type database, and the database is of kind linear, and so this resource must be used linearly, and when it's closed you can't use it anymore. On the contrary, here we have the math string, and string are unrestricted, and so you can use them in unrestricted fashions. Furthermore, we have borrows, so as present in Rust and other languages, borrows allows to do imperative programming very conveniently, and that's why we use them here. Finally, a final specificity of AF is that we have complete type inference. So before I used a type annotation here to simplify, to make it easier to read, but I don't need to. Here, type is completely inferred by the type checker. So to present AF, I'm going to go through various of its features, and I'm going to start by linearity. So as I said before, kinds determine usage. We have three kinds. Linear, a resource must be used exactly once. Affine, a resource must be used exactly at most once, so 0 or once. And unrestricted, the object can be used arbitrarily many times, from 0 to infinity. Here are a few examples. We have a database type of kind lin, a string type of kind unrestricted. We can also have parameterized kind, so for example a list as the kind of its content. If we have a list of database, then it must be used linearly. If we have a list of string, it can be used unrestricted, in an unrestricted fashion. To use this kind of parameterized kind, we also have kind constraint. So here we have the type function create list, which takes an element and replicates it multiple times to create a list. Since the element is going to be replicated, then naturally its content must be unrestricted, and that's exactly what this constraint says. Finally, we also use subkinding. So un is smaller than af, which is smaller than lin, and that means that if a function only expects linear objects, we can pass it unrestricted objects. And the reason is that if something can be used in unrestricted fashion, in particular it can be used linearly. This is the base of our language, and we're going to use it to build up everything else, and in particular functions and captchas. So Here's a piece of code where we open the grade database, then we create a function that logs some message and then close the database. As you can see, we have a capture here. The log and close function captures the grade database. And grade database is linear. It must be used exactly once. And so the log function must also be called exactly once. If we ask the AF type checker, it's going to give us this type, string, arrow annotated by lin, and unit. And the annotation on the arrow indicates the usage mode of this function. It indicates that log and close must be called exactly once. A fair warning, to make everything clear, this annotation does not say anything about the argument. Here, the argument is of type string, so it's unrestricted. You can do whatever you want with it. The arrow, and in particular this linear arrow, is not a lollipop from linear logic. It only says something about the function itself. Alright, so we can do nice functional programming with all this. Let's look at imperative programming, and for that we need borrows and regions. As in Rust and other languages, a borrow is a temporary loan of a resource A, and we have two types of borrow. Shared borrows are for observing the resource, and exclusive borrows are for modifying the resource. Here is an example of a correct use of borrow. We start by looking up two grades concurrently, so this is a read action, so we use a shared borrow for observing the database. Since it's shared, we can look up two things at the same time, concurrently, and in particular the kind of this is unrestricted. Once we are done with looking up these two grades and making their average, we can write in the database using an exclusive borrow, and exclusive are, as I said, exclusive, and they have in particular the kind affine. So there are a few rules to use these borrows. The first rule is that you cannot use a borrow and the resource itself at the same time. Here, the f function is called with the resource and a borrow, and that's not allowed. The type checker will reject this. A second rule is that we cannot use an exclusive borrow and any other borrow. Here I have an exclusive borrow and another borrow, and the type checker will again reject this. Finally, a borrow must not escape. Here we have a declaration of a database and then a pair composed which contains a borrow, and then we try to leak the borrow while the database is still captured inside the function. So this is not allowed because the borrow is escaping its region, and here is the region delimiting the borrow. So the regions are almost lexical scoping with a few tweaks. And the way we check for this kind of escape is by using the indexed kinds. So before I said the kinds were unrestricted, affine, and linear. Actually there are a bit more. They're indexed by their nesting. And here the grade, the borrow of the database is in the second nesting, so it's annotated by un2, whereas the region around it is at the nesting level 1. And so we will simply check 2 is bigger than 1, so the borrow cannot escape. And the type checker will again reject this. Alright, so we have borrow, we have closure, we have functions, we have linearity. Let's put everything together. Here is the API for the database that I've used since the beginning of this talk. The type database is of linear kind. We have the find function that takes a borrow with its kind and takes a string and returns an integer. We have the add function that takes an exclusive borrow, a string, an integer, and returns unit. And since the functions are purified, you can here database borrow is captured later on, and so the functions are annotated with the kind that is captured here. Here is a simple use of this API, as I said, which was presented before. So we have two concurrent lookup, grade DB, of the grade DB of two grades, math and comp-sci, and then we compute the average. We can factorize a little bit the lookup aspect by creating a grade function that captures the database and look up the topic or the subject of the grade. And here we repeat the argument, subject and subject. So we can simply partially apply the function and it will compute the borrows and the kinds accordingly. And finally, we can even go further and use some functional abstraction to pull the function computing the average outside by taking a list of subjects and applying a partially applied function in list.map and so on and so forth, and use high-order functions as we would want to in a functional language. The type checker will annotate the region as we would expect. Here are the disjoint region for the shared borrow and the exclusive borrow, and they are properly disjoint. Finally, as we said before, we have no type annotation. So even if I used the average, even if I lifted the average function out, I still have no type annotation here. We have complete type inference. All right, so let's look a little bit under the hood at inference and constraint. The first step is to elaborate the region by using the information provided by the position of the borrow, the scopes of the borrow, and the borrowing rules I presented, which allow us to completely determine the biggest region we could use. The second step is to generate constraints which will encode type, linearity, and borrowing checks, and to check that nothing escapes that shouldn't. This constraint system is custom to encode the rule we want and based on HMX. Finally, we solve the constraints using a custom algorithm that we provide, and we obtain principal type schemes for all the functions in our program. So this principal type scheme can sometimes still be a little bit complicated, and so we use subkinding rules with positive and negative position to simplify the type further down. Alright, and so we obtain finally the simple type schemes. So to summarize, I presented the AF language. A prototype is available at this address online. We provide linearity, closure, borrows, and region to provide good support for both imperative and functional programming. We support managed and unmanaged object and principal and type inference, which is something very novel for languages that support borrows. The downside is that so far we do not support real flow sensitivity. We can emulate various bits, but it has no proper support. And we do not have yet a concurrency story, so that's something we are working on. In the paper, you can find many examples to show that we can indeed support many types of programming, both functional and imperative. On the theory side, we provide a syntax-directed type system for AFA, or to encode into an ML-style type system. We provide a formal account of the semantic and its proof of soundness, and an inference algorithm for AF, which provide various novel contribution, in particular an extension to HMX, novel constraint system, and its constraint algorithm and proof of completeness. That's all I have. Thank you very much.
So thank you, Gabriel. So if you want to join the author for a live Q&A, click on the link in the Slido room for this paper.